Hello and welcome to Nerdy Nisa. Today we're going to be going through how to prove trig identities. We're going to go through some general steps that I generally find helpful, and then in the next video we're going to go through a bunch of different examples just to get the practice going. But before we get into any of that, what does it mean to prove a trig identity? It means that you're proving that the left-hand side is always equal to the right-hand side for any value of the variable you're talking about. So those ratios are definitely a truth and they can definitely always be equated. So an algebraic example of this is if I have something like 12 minus 5 equals to 7. I know that no matter what, the value of 12 minus 5 will always be 7, and 7 will always be equal to 7. So this would be an identity, because I know if I have 7 in an equation, I can sub in 12 minus 5, and it would not change the value of that equation, because those two things are definitely equal. Let's look at the first step here. It tells us that we need to assess our ratios. Now by that I mean, look at the types of trig ratios you have on the right-hand side and allow that to inform what you do on the left-hand side and what ratios you're going to attack. By ratios, we're talking about things like sine, cos, and tan, because those are our trig ratios. That's just a bit of jargon there. Cool. So what I mean by that is that generally we like sine and cos. We're quite discriminatory when we talk about math. Like we love sine and we love cos. These are our best friends. But we don't like tan. When tan comes along, we are not too good of friends with tan. So that means that whenever you have some sort of like a trig identity to prove, you can only justify keeping tan in the left-hand side that you're changing in the instance that you have tan on the right-hand side. Because otherwise, you don't want tan in your identity, you don't want to be using it, so it's not worth keeping. So let's look at an example to put this all into context. Let's imagine that I have 1 over cos x minus tan x times sine x, and I want that all to equal to cos x. If that's the question, then I know I need to manipulate my left-hand side to make it look exactly like my right-hand side. Now, as you can see, we're working with sine and cos. Yippee! Remember, we love our sine and cos, but we don't like tan. So when I see this tan over here, I must go, I don't want tan here. And would you look at that? On the right-hand side of my equation, on this side here, because this is the right-hand side, right? For the right-hand side of the equation, there's no tan there. There's no way that I can justify having a tan there. So because I don't like tan, it's not even on the right-hand side, I need to change this ratio. So this is just a nice way to know where to start, because you generally start by converting tan ratios because you want to be working with sine and cos. I mean, if there is a tan ratio on the right-hand side, then you leave it in and you adjust the other ratios, but just looking at the ratios helps you know where the starting point is. The second step here is to sub in your identities. So this means that we have a bunch of different basic identities that we generally accept as universally true. So I can use those identities to kind of remodel my left-hand side. So that looks like our reciprocal identities as a starting point. Reciprocal identities are things that say 1 over sine theta is equal to cosec theta, and 1 over cos theta is equal to sec theta, and 1 over tan theta is equal to cot theta. Generally, when working with proving identities, we don't really like these reciprocal fellas because the rest of our identities aren't really written in terms of them, so they're just harder to use. So we would generally, as soon as seeing these fellas, want to convert to their left-hand side counterparts. So if you see sec theta, sub in 1 over cos theta so that you have something easier to work with. The second thing that you can look at is essentially our identity pyramid. Now this pyramid, if you're used to multiplication pyramids, is really easy to follow because it says sine theta is at the top, cos theta is at the bottom, and so is tan theta. So from here I can derive that sine theta is equal to cos theta times by tan theta, and that cos theta is equal to sine theta over tan theta, and that tan theta is equal to sine theta over cos theta. And that's really helpful because if you want to swap and change the types of ratios that you're talking about as per the first step that we talked about before, then you can use these to kind of relate the different ratios to one another. The next kind of identities are ones that involve some squares. So these are like the square identities. They're really cool, and you're going to end up using them quite often. The one that you're going to use the most is the one that tells us that sine squared theta plus cos squared theta is equal to 1. From here, you can derive the two different versions of this, in which you have sine squared theta is equal to 1 minus cos squared theta by just moving the cos to the other side, and that you know that cos squared theta is equal to 1 minus sine squared theta, and you know this by moving the sine to the other side. So that's just a really cute way for you to be able to convert sine squared to cos squared and just play around with those identities a bit more. Now, the last types that go under these square type identities are the ones that involve tan. So if you do have tan on the right-hand side and you're going to end up keeping it, then these ones can be particularly helpful. So you have the identity that tells us 1 plus tan squared theta is equal to 1 over cos squared theta, and the identity that tells us that 1 plus 1 over tan squared theta is equal to 1 over sine squared theta. These ones are a bit trickier and you won't use them as much, but still useful to have in your back pocket. Lastly, we're going to understand that we need to use regular algebraic techniques to simplify the left-hand side. Now, when I say regular algebraic techniques, I mean things like factorizing, like multiplication, like division, all of those things. And under factorizing, you've got a whole bunch of different things. You can use your grouping techniques, you can use highest common factor and removing it, and all of those are going to come into play. So I would just revise that as well, just so you know essentially what tools you have in your toolbox to try and remodel that left-hand side to make it look like the right-hand side. And part of this also then becomes the idea that I call the mind map method. Now, this method is essentially to say that we're not always going to know what route to take. So whether it be which identity to sub into, or whether it be which algebraic technique to use, it's not always going to be 100% clear to you as to which route you take to prove this identity, especially when you're starting out and it's like really, really tricky to understand kind of the intuition that goes with proving your trig identities. So the mind map method is essentially when you have some sort of trig identity, you have the left-hand side and that's supposed to equal the right-hand side, and you can see that there's multiple ways that you can approach the left-hand side. I would then, in pencil, branch out those different ways, whether that looks like subbing in different identities. So, for example, if I have something like sine squared theta, I know that I could either make that equal to 1 minus cos squared theta, or I could make this equal to tan squared theta times by cos squared theta. So I know that there are two options that I have available to me. And let's say I have like cos and tan both on the right-hand side. Now I don't know which one to pick. So what I would always recommend doing is splitting up the different options. So have the 1 minus cos squared theta as the one option over here, and have the tan squared theta times cos squared theta as the other option over here, and just kind of play down and play around with them going downwards and like write out the simplification of each different version of it, and then you're going to see pretty soon which ones are viable and which ones aren't. So the ones that aren't, you can pretty much eliminate. You can be like, oh no, those ones aren't valid, and the ones that are valid, you can pick between which ones you want to write in pen. Now note, any way that you try and flip it, in the end, you can definitely prove the identity because you're using things that are truths, because you're using other identities to help prove those identities. But we're just looking to try and distill what's the easiest route that we can take, because you don't want to be taking some really complicated route and then trying to thug it out in pen, and now you run out of space and realize you have to backpedal because it's getting too complex. So there's generally going to be like one or two routes that are easy and simple and both viable, and then there's going to be a couple of other routes that you could take that just aren't going to work out very easily, and it's going to take you a long time to get there. And that's essentially how the mind map method works, just so you can explore your options and fiddle around with them a bit more. Thank you so much for watching this video. I hope that it really helped. If not, and you have any questions, please leave them in the comment section below, and I'll try and help as best as I can.